discussion of operational amplifiers and in addition we shall consider diodes. As you recall, on the last occasion we had introduced the model of an operational amplifier as having two inputs and one output. The two inputs are marked with negative and positive signs. The gain capital A is written inside the triangle. The first is the inverting input, the second is the non-inverting input, and this is the output. And the model of the op amp is that if the two inputs are Vn and Vp and the output is V0, then V0 is equal to capital A Vp minus Vn, where capital A ideally tends to infinity, Rn, Rp and Rnp, which respectively denote the input resistance looking into the the input resistance looking into the inverting terminal, input resistance looking into the non-inverting terminal Rp, and the input resistance looking between the inverting and the non-inverting terminals Rnp. All of them tend to infinity. Input resistance is infinite, so that the op amps do not take any current at their input, and the output resistance tends to 0. This is the situation for an ideal op amp, and with this definition and assumptions about an ideal op amp, we analyzed a simple amplifying circuit in which the non-inverting terminal is grounded and input is applied to the inverting terminal through a resistance, let us say Ri, and there is feedback, that is, there is a connection between input and output through another resistance Rf, and this output is V0. We argued that if the op amp is ideal, that is, if capital A tends to infinity, then the potential difference between this point and this point should be approximately 0, and therefore this point, although not connected to ground, behaves like a ground, and therefore this point is known as the virtual ground. Now, if this is a virtual ground, then obviously the input impedance Rin, input resistance looking from here, which is the ratio of the voltage applied here to the current that goes in, is obviously equal to Ri. The input resistance as faced by a source connected here shall be equal to this, and V0 by Vi, let us call this Vi, V0 by Vi, which is the gain of this configuration. We showed that this is equal to minus Rf divided by Ri. Alright, it is simply determined by two resistances. If you want, this gain is obviously a inverting gain because the polarity is negative. That is, if Vi is plus 1 millivolt, then V0 would be minus 1 millivolt multiplied by the gain factor Rf by Ri. Alright.
That means that in this case the relation V0 is equal to A Vp minus Vn doesn't hold.
It does.
So then sir, if it does hold, then A must be equal to minus Rf upon Ri.
The relationship is this: the potential difference between these 2 points, let us call this as some value, let us say mu. Then V0 is given by A times, if the polarity is like this, A times nu. Alright. Since we have assumed capital A tend to infinity, nu tends to 0. This was the assumption. Now, the gain that we are now talking of is not what is applied at the inverting terminal or non-inverting terminal directly, it is applied through a resistance, and therefore the total amplified circuit is this. It is V0 divided by this Vi, not what voltage appears here. Agreed? The definition of an op amp remains the same. It is A times the voltage applied to the non-inverting terminal minus the voltage applied to the inverting terminal, and because of our assumption of ideal op amp, the input voltage between the inverting and the non-inverting terminal is equal to 0. All right, does that make clear? If you want a non-inverting gain, then as you can guess, our input shall be applied to the non-inverting terminal. Let's draw it up to show this carefully, to show this clearly. Suppose there is a voltage Vi here. What we want is a non-inverting gain. In other words, we want a V0 which is equal to a positive quantity multiplied by Vi. Then the configuration is that from the inverting terminal you provide a path to ground through a resistance, let us say R1, and a path to the output through a resistance, let us say R2. This circuit, as we shall show in a minute, acts as a non-inverting gain amplifier. Now the analysis of this circuit becomes extremely simple if you take account of the fact that the potential difference between this point and this point should be approximately 0, and therefore the potential of this point should be equal to Vi, because the drop here is 0, this potential should be Vi, and therefore as far as V0 and Vi are concerned, there is simply a potential division between R2 and R1. In other words, Vi should be equal to V0 times R1 divided by R1 plus R2. Agreed? You see how simple the analysis is? And therefore the gain G which is equal to V0 divided by Vi, is simply equal to R1 plus R2 divided by R1, which is equal to 1 plus R2 by R1. The gain is greater than 1. All right. Notice that the sign of the gain is plus, positive, as expected, because the input is applied to the non-inverting terminal, and therefore it does not invert.
So how do you get Vi is V0 times R1 by R2?
Oh, look at this path. Look at this path. The output impedance of the amplifier is ideally 0, and therefore this point acts as a voltage source. The equivalent circuit would be, there is a V0 here, plus minus, this goes to ground, and this comes to R2 and R1, and this is Vi. All right, that is how we wrote this relationship. However, there is implicit in this relationship another important assumption, that the op amp at the inverting terminal does not take a current. Isn't that right? Suppose there was a current here, then this relation would not have been valid. This relation assumes that whatever current comes here flows like this, right? If there was a current here, then the relation would not have been valid. Then your KCL would require that this current should be equal to this current plus the current going through there. All right. So this relationship is valid if the op amp is assumed to be ideal. The idealness is reflected in three things. One is that as far as the output of the op amp is concerned, it can be considered as a voltage source, as an ideal voltage source. Suppose it was non-ideal, then obviously you should have included here the R0, right? And then this relation would not have been valid. So it assumes that the op amp is ideal, the output resistance is 0. It assumes that the input resistance is also is infinity, that is the input resistance infinity, that is the op amp does not take any current at the inverting terminal. What is the third assumption? Third assumption is capital A goes to infinity, so that this potential cannot be different from this potential. Vi comes here. All these assumptions are involved in this relationship. All right. And so in practice it will be slightly different from 1 plus R2 by R1. Actually it will be higher or lower. It will be lower than this, because the op amp shall take a current, the output resistance shall not be 0, and capital A shall not be infinity. So the actual voltage gain will be slightly lower. But this relationship is one of the key relationships. Now you notice that in the inverting amplifier configuration, what was the input resistance faced by the source? It was equal to Ri, that is the resistance connected. So it is not infinity, it is finite. On the other hand, in the non-inverting configuration, what is the input resistance faced by Vi? Infinity. Isn't that right? So this is an important difference between the two connections, non-inverting and inverting. In the non-inverting configuration, the input resistance is maintained at infinity, whereas in the inverting configuration, the input resistance is determined by an external resistance that is connected between the source and the inverting terminal of the op amp.
So
Why?
why do we do this?
Why do you do what?
So we connect resistance in this case and not in that.
We want a non-inverting gain. We want a non-inverting gain, then this is the configuration. We want an inverting gain, then the previous circuit that we drew, this is the configuration. Why do we do that? We want to get a certain gain, and so we determine the gain through two external resistors, RF and RI. All right.
So what will happen if in the inverting configuration we don't have an external resistance?
We don't have RI.
Yeah.
Okay, then the gain shall be infinite. What happens then? If Ri is not there, Vi is applied directly here. All right, directly at the input terminals of the op amp, which means that if it is multiplied by A, which goes to infinity, your V0 shall go to infinity. But as I said, V0 in a practical op amp cannot go to infinity. It is limited by the power supply. So if the power supply is plus minus 12 volt, V0 will saturate. It wants to go beyond 12 volts, plus 12 or minus 12. All right. So it cannot go. It saturates at either plus 12 or minus 12. So if you apply directly, let's say 1 millivolt source at the op amp input terminals, what you will see at the output, if you put in a CRO, the baseline will go up plus 12 or go down by minus 12, and it will stay there. So it saturates. Yes, is there any other question? Okay, now look at this configuration again, and suppose R2 is equal to 0. Suppose R2 is equal to 0. In other words, this is directly connected, then the gain becomes plus 1. Is that correct? And therefore it is called a unity gain configuration, unity gain. This deserves a little more closer look. So let's draw it again here. Now if R0 is 0, if R2 is 0, do I have to put an R1? You see, the gain is 1 plus R2 by R1. If R2 is 0, R1 can as well be infinity. Isn't that right? And therefore I don't need to put an R1. Is that clear? And therefore this is the simplest possible op-amp circuit giving a gain of +1. You might ask, why should we get a circuit with a gain of +1? Well, it provides isolation. You see, if we apply a voltage source here, okay, then the output and input are isolated because this voltage source does not deliver any current, but you are transferring the voltage source here. It is actually a transfer from input to output, and the two sources then become isolated with respect to each other. The simple equivalent circuit would be this: Vi. Can Vi be allowed to have an internal resistance? Can the source be allowed to have an internal resistance? Oh, why not? The op-amp doesn't take any current, so it could be any internal resistance. Any internal resistance, let us say Rs. And at the output you simply get V0, which is equal to Vi, because the gain is unity. Alright. Now you see that if I connect a load here RL, then the current in the load would be Vi divided by RL. On the other hand, if I had connected it directly here, the current would have been Vi divided by Rs plus RL. In other words, a load would affect, the current in the load would depend on Rs, alright, which is not the case here, because Vi, whatever the source impedance is transferred directly to the output, and therefore the load current or the load voltage shall remain Vi irrespective of what Rs is. So it provides an isolation between the input and the output, and in that sense it is given various names: isolating stage, or more popularly it is known as a buffer stage. Buffer between the input and the output, the op-amp acts as a buffer. It is also called a unity gain amplifier, UGA, unity gain amplifier, or it has got various names. It is also called a voltage follower, that is, the output voltage follows the input voltage, and therefore it is called a voltage follower. It is a very important circuit to get a gain of +1. One more question that one should ask at this stage is, the gain here is 1 plus R2 by R1, that is, it is greater than unity, whereas the gain in the inverting configuration was minus Rf by Ri, which could be less than 1 or greater than 1. It could also be equal to -1 if Rf and Ri were equal. Is the point clear? If Rf and Ri were equal, the gain would have been -1. If Rf is less than Ri, the gain would have been less than unity. If Rf is greater than Ri, the gain is greater than unity. Whereas in the non-inverting configuration, it appears that you can only have a gain either 1 or greater than 1. The question is it possible to have a gain less than 1? The answer is yes or no? Yes. How do you get a gain less than 1? What? Negative resistance? Oh no. That's a mess. Getting a negative resistance, you have to use another 2 or 3 op-amps to get a negative resistance. Can't you suggest a very simple procedure? Why don't you, before applying to here, why don't you attenuate by the required factor? Alright. Suppose I want a gain of half. Then what I do is I make R2 equal to 0, R1 equal to infinity, and then I use a potential divider here. That's it. I can reduce the gain to half, but in the process I also lose something. What is it that I lose? No, it's not energy. I lose the advantage that the input impedance now no longer becomes infinity. The input impedance will be the sum of these two resistors. Is that understood? The source has to be connected here instead of here. If I want a gain less than 1, then the source has to be connected here. So what the source sees is the sum of these two resistances. The op amp does not take any current, so the infinite input resistance advantage is lost. But it is possible to retain infinite input resistance and also to achieve a gain which is less than 1 in a circuit which shall be experimented upon by you in the laboratory. And that is an interesting circuit. If you cannot understand it, maybe I will explain later on. Then we consider another application of the op amp in summing several voltages, in adding up a number of voltages, and the circuit is very simply this. What we have is the non-inverting terminal is grounded. We have a number of sources, let us say V1 connected to the inverting terminal through a resistance R1, a voltage V2 let us say connected to the same terminal through a resistance R2, and so on up to let us say n number of sources Vn connected to the same point through a resistance Rn. In addition, there is a resistance from output to input, let us call this Rf. Alright. There is a number of voltages V1, V2 up to Vn, n number of voltages connected to the inverting terminal through a series of resistors R1, R2, Rn, and from between the output and the input there is a resistance Rf, the feedback resistance. To analyze this circuit, notice again that if this is V0, then the current through this would be equal to V0 divided by Rf, because this point is virtual ground. Alright. So this current shall be V0 divided by Rf. Similarly, you can find the currents through each of these resistors. Because this is virtual ground, the current here would be V1 by R1, the current here would be V2 by R2, the current here would be Vn by Rn. Alright. And therefore, what you get is by KCL V1 by R1 plus V2 by R2 plus etc. plus Vn divided by Rn plus V0 divided by Rf, this should be equal to 0 by KCL, and therefore you can find out the value of V0, the output voltage, and simple algebra shows that the output voltage V0 is equal to minus, there is a negative sign. Why is the negative sign? That is expected because you are applying to the inverting terminal, negative sign, then you have Rf divided by R1 times V1 plus Rf time divided by R2 times V2 and so on up to Rf divided by Rn times Vn. And you see that this is not a simple addition, this is a weighted addition of various voltages, weighted addition. V1 is weighted by Rf by R1, V2 by Rf by R2. For example, you may want 0.1 V1 to be added to 10 times V2 to be added to let us say 7.5 times Vn. Then you choose an Rf and you choose R1, R2, Rn such that you get these factors. So it is a weighted addition. This is, for example, you may want this to be, this addition to be made, 0.1 V1 plus 10 V2 and so on and so forth. Alright. So it is a weighted addition, of voltages. If you simply want to add them, then you make all resistors equal. Alright. Make Rf equal to R1, Rf equal to R2, Rf equal to Rn, and therefore you will simply get V1 plus V2 plus Vn and so on. Alright. What is the input impedance? faced by V1 for example, R1. Similarly, each voltage source faces the impedance or the resistance that is connected between it and the inverting terminal. Alright, that is the input resistance. Now, suppose we don't want this negative sign, we want an addition with a plus sign. What is it that we can do? You can use the inverting terminal, non-inverting terminal. Yes, you can do that. What you can do is, let's find an alternative solution first. Suppose I am stuck with this. Let's say I have a chip which does this, and I want to use this chip. There is a negative sign. I want to change the sign. What do I do? That is correct. You take an op amp with a -1 gain, which is simply this op amp. Minus, plus, this is grounded, and this resistance is the same as this. So what all I do is I cascade, or I connect in cascade, connect in tandem another stage like this, and then this is simply a sine inverting stage. That means a stage with a gain of -1. I can either do this, or if I am fussy, I don't want to use two op amps, then what I will do is I will connect these sources here. V1, V2, Vn, R1, R2, Rn. Then what do I do? Can I leave this open? No. Why not? That is the question I have not raised so far. I wanted to come to a certain stage. Can I, for example, ground this? Oh, I cannot do that, because an operational amplifier, because of the high gain, can never be left open circuited. Except in very special situations, we cannot leave it in an open loop. That is, we must have, we will clarify this later in great details, a high gain amplifier should always be operated with feedback, and feedback should be negative feedback. Suppose I connect a resistance from here to the output terminal, you will get nothing. The amplifier will start oscillating, it will give all nonsense, it will be unstable. So there must be a feedback from here to the output. So the output is here, there must be a feedback like this. Now, what will this feedback do? Suppose this resistance, well, call this resistance as some RF. What would be the gain from here to here? From this point to this point, what will be the gain? I have done this configuration a minute ago. What will be the gain from this point to this point? The gain +1. Don't you see that this is the same circuit as this? There is an R1, but that R2 is infinity. The gain is 1 plus R1 divided by R2. R1 is there, non-zero, but R2 is infinity, and therefore the gain is +1. Is that clear? So, what we are basically doing is we are using a unity gain stage. The addition is done right here. The addition is done right here, and the gain from here to here is +1. If it is +1, do I require the RF? No, I don't require. So I can as well short circuit this. Or if you want a gain, suppose you don't want a unity gain, you want a gain greater than 1, then what you do is you connect a resistance from here to ground. Suppose this resistance is G, RG, then what is the gain from here to here? 1 plus Rf divided by Rg, and whatever the voltage addition occurs here this will also be a weighted addition. I leave this to you as an exercise to find an expression for V0 in terms of V1, V2 and Vn. Alright, you can do it by summing up all the currents here, V1 by R1 plus V2 by R2 plus Vn by Rn. What will this current be? Total current. It shall be equal to 0. Alright. And what is this voltage? What is this voltage? How come? It would be V0 Rg divided by Rg plus Rf. And because no voltage can exist between these two, this voltage shall be the same as V0 Rg divided by Rg plus Rf. So equating these two, you can then find out the voltage V0 in terms of V1, V2, Vn. This is one method. Another method is superposition. That is, you find out the effect of V1 on V0 by killing all other sources. Killing means what? They must all be connected to ground, because the sources have to be short circuited. So you find V0 1 due to V1 alone, then you find V0 2 due to V2 alone, and sum all of them up. Whatever way you do, you should be able to get the correct result, and I leave this to you as an exercise. Let us consider now another circuit as an example of application of the op-amp. Let us have a Vs, a voltage source Vs, in connection with, in series with its internal resistance, let us say Rs. Okay, we have a voltage source in which is not ideal, which has an internal resistance Rs, and we connect it to the non-inverting terminal of the op-amp. All right. As I said, an op-amp cannot be left without negative feedback, because then it will oscillate, and therefore to be able to operate this to the inverting terminal, you must connect, depending on what you want, you must connect a resistance from input to output, and then suppose there is another resistance here, and let us call this R1 and let us call this as R0. All right. Now what would be this potential for the analysis of this circuit? What would be this potential? Vs. Why? Because the op-amp does not take any current, so there is no drop in Rs, so Vs comes directly here. Is this point clear?
Yes, sir.
All right. If this is Vs, then what is this potential? Vs. Then what is this current? Vs by R1. All right. What is this current? Okay, let us call this current as I0, then I0 is Vs by R1. All right. Now what is the equivalent circuit? Equivalent circuit of this is that you have a Vs, it is with an internal resistance Rs, it does not deliver any current. The output current I0 is equal to Vs divided by R1. All right. This is the circuit. Don't you see that this is a voltage controlled current source? All right. So this is called a voltage to current converter. Voltage to current converter. A voltage Vs is being converted into a current which is proportional to Vs, and the technical name for such a converter is a transducer. A transducer converts a physical quantity into another physical quantity. For example, force could be converted to a voltage. The device that is used is a transducer. A voltage is converted to a current, both electrical quantities, but the nature of the quantities are different. One is an across variable, the other is a through variable. So it is called a voltage to current transducer, or simply VCT. Similarly, you could have a CVT, current to voltage transducer. We shall see this later, but transducer is a general term. A transducer is a device which converts one physical quantity into another physical quantity. The two quantities could be quite different from each other. In that sense, is an op-amp a transducer? Op-amp, is it a transducer? No, it converts a voltage into a voltage, but an op-amp along with peripheral circuits like this can act as a transducer. It can convert, yes.
So why is I0 Vs by R1?
Why is I0 Vs by R1? Because the op-amp does not take any current here. This current is 0. Therefore, whatever current is flowing here must come from here. That is the simple explanation. We shall come back to op-amps later when we have done a little bit of transistors and transistor circuits. We shall come back, but as far as the laboratory is concerned, this knowledge will be sufficient to carry out experiments with op-amps. We next consider another very simple device called a diode. A diode has already been introduced as a nonlinear device which conducts preferentially or in a discriminatory manner. It conducts in one direction, current in one direction more easily than in the other direction. That is, a diode, if it is connected like this, if it is diode, the symbol for a diode is this. The left side is called an anode and the right side with a vertical line is called a cathode. This is an anode, this is the anode and this is the cathode. From anode to cathode, it conducts a current easily. This is the direction of the current. On the other hand, if the polarity of the battery is reversed, the current reduces to a very small magnitude. And as I had shown in a few classes, in a class held a few days earlier, the operating characteristics or the VI characteristics is like this. Excuse me. Is this the voltage? Yes, this is the voltage and this is the current. The current flows easily if V is positive, whereas the current flows with a lot of reluctance if V is negative. This current, when V is negative, this current is negligibly small. In fact, the forward current could be of the order of a milliamp and the reverse current could be as small as a nanoamp. Nanoamp is 10 to the minus 9 amperes. All right. Now, exactly like an op-amp, we would like to idealize a diode. And ideal characteristic of a diode, I idealize it by saying that the reverse current is 0. So the ideal characteristic is that it remains 0 like this, and when V is positive, well, the current increases without bounds. That is, this is the ideal characteristic of a diode. Now this ideal characteristic, doesn't it remind of a switch, that when the switch is on, any amount of current can flow, when the switch is off, no current can flow. So an ideal diode is equivalent to a switch. When the diode is biased in the forward direction, that is, the anode is positive with respect to the cathode, the switch is closed. When it is biased in the reverse direction, that is the anode is negative compared to the cathode, then the switch is open, no current flows. And therefore, if an ideal diode is simply connected, one should not do that, but on paper there is no harm. Suppose an ideal diode is connected like this, an ideal diode, then the current in this circuit shall be infinite. So, the diode shall burn. And there are many diodes which are very nearly ideal, and one should never make a connection like this. A diode should never be connected across a battery directly, because even if it is not infinite, the current may be large enough to burn out the diode. All right. So, what then limits the current in the diode? Obviously, we shall have to have an external resistor in the circuit. All right. So, a diode, a typical diode circuit would be like this. You have a voltage source, let us say V, and then you have an R. If this diode is ideal, then the current in the circuit would be like this, and the current would be simply given by V by R, because the diode in the forward direction acts as a switch with zero resistance. We assume, what is the drop in the diode then if it is ideal? 0. The total drop shall be across R. All right. Now, this preferential flow of current in a diode is utilized to convert an AC to DC. Suppose you have an alternating voltage like this. If it is applied, if this V is replaced by an alternating voltage, let us say Vm sin omega t, then the current in this circuit shall flow only during the positive half cycle, that is only during this cycle, while the current shall be determined by the external resistor R, and therefore, if this is Vm, if this is V, if this is V, then and this is I, then the I during the negative half cycle shall be equal to 0. Isn't that right? And for the next cycle again, the current shall be positive, current shall flow, and then the current shall not flow. So, if you have an alternating voltage like this, Vm sin omega t, then the current in this circuit is pulsating. It consists of half sinusoid pulses only during the positive half of the voltage. Therefore, a bidirectional voltage, a voltage which could be positive as well as negative, is being converted into a unidirectional current. And by dropping the current in a resistance, you are converting this to a unidirectional voltage. However, this voltage is not constant, it is pulsating, it varies. The average value of this obviously is a DC voltage. All right. So, this voltage, let us now consider the voltage, only half cycles. This voltage can be thought of as an average voltage, like this, on which is superimposed an alternating voltage like this. All right. We can think of like this. And usually what we want is if you want to convert AC to DC, what we want is this violet line. We don't want this AC superimposed on the violet line. So, this AC, we want it to be as small as possible, and therefore, we call this as a ripple on an otherwise calm water surface. If you make a small disturbance, then there are very small waves. This is what we would like. We would like a ripple to be as small as possible. Now, a diode used in this manner is called a rectifier. It rectifies the AC voltage to a unidirectional voltage, all right. A diode connected like this, and since it converts only half of the wave, the other half goes waste. We are not doing anything to this. Other half is simply blocked, and therefore this is called a half wave rectifier. A half wave rectifier, all right. Now, a half wave rectifier converts an AC into a pulsating DC. There is a steady component upon which is superimposed an AC. We want to get rid of the AC, all right. If you want a pure DC, we want to get rid of the ripple, and this is done by a circuit known as a filter. A filter, that is, it is a circuit which retains the DC and filters out the AC. Now, the filter usually consists of energy storage elements, inductance or capacitance or both, L and C. It could be both. So, what we do is, suppose we have a half wave rectifier, which is connected to an AC source Vm sin omega t. The output is passed through a filter, then the output of this shall be hopefully pure DC voltage, and this is what the power supply that you see in the laboratory gives you. And this combination of a rectifier, as you will see later, a rectifier could be half wave or full wave. We can use diodes, more than one diode in a connection, such that the other half, the negative half, is flipped to become positive, and the other half is also utilized, all right. So, any rectifier connected to a filter to filter out the AC or the ripple, the total combination is called a power supply. The total combination is called a power supply. The output of this hopefully would be a pure DC, but pure DC from such a combination is also an approximation. You shall always get a DC along with maybe a very small ripple. It could be, let us say, 0.01% ripple, all right. So, the efficiency of such a device is characterized or measured or specified in terms of what is known as a ripple factor, which relates to the amplitude of the ripple to that of the DC. For example, if the DC voltage required is 100 volt and the ripple is, let us say, 0.1 volt, then we say the ripple factor is 0.1 divided by 100, or sometimes specified in terms of percentage. We simply say the ripple is 0.1%, all right, 0.1 in 100. Yes.
So when the AC is rectified fully, so then when we talk of the average value of the current, is it over the entire time period or half the time period?
Whenever the average value of a pulsating DC is to be found out, it is over the complete period. It is no longer a pure AC now. If it is a pure AC, then the average value is 0, and for a pure AC you talk of average value over half a cycle, all right. When we talk of a rectified voltage which is already unidirectional, we talk of the average over a complete cycle, and therefore it follows a profound statement that a full wave rectifier, the DC that it shall produce will be twice the DC produced by a half wave rectifier. Is that clear? We will look into this mathematically in more details next time.